Welcome to Complex Analysis Lesson 13 on logarithms. We're going to go over the complex version of logarithms, give a few examples, and explain some of the differences between the real valued logarithm and the complex version case. The complex logarithmic function is defined as the inverse of the complex exponential function. So if we let z equal e to the w, where w is a complex number, then we define log of z equal to w. So the log is actually the exponent. That's true for complex as well as real valued logs. And since e to the w is never 0 and e to the w is z, then that means z does not equal 0. It's a condition on the log of z. We can write z in polar form. Here, r e to the I theta, where r is the modulus of z. And then we can write z using the definition of w here. We can break this as the product of e to the u times e to the iv. So if we just look at the modulus here, r equals e to the u, which implies just from real valued logarithms that u equals the natural log of r. So that gives us the first part of our logarithm. Now the second part is we need to find what v is in terms of the argument. So v does equal the argument of z, but from lesson 2 you might recall that the argument is a multi-valued function. So we have the principal value of the argument, which is between minus pi and pi, or you could define it between 0 and 2 pi, plus 2 pi n. So it repeats every 2 pi n, where n is an integer. So putting these pieces together, we have, by definition, our log of z, complex log of z, equals the natural log of the modulus of z plus I times v, so it's I times the principal argument of z plus I 2 pi n. So this is our log. It's based on the real value log function, and then this repeating argument every 2 pi n. Okay, just repeating what I said on the previous slide, the log of z equals the natural log of the modulus of z, so this is the real valued natural log, plus I times the principal argument of z, and as I mentioned, it's either between minus pi and pi or between 0 and 2 pi. In this case, you have a discontinuity along the negative real axis. In this case, you have a discontinuity along the positive real axis. And it's possible to pick other ranges of size 2 pi depending on the particular problem at hand, but we'll just look at these two for the moment. Yeah, so when n equals 0, then we're using what's called the principal value of the log. So when n equals 0, this drops out and you just have the log z equals these first two terms here. And this is known as the principal branch, and you write that with, or at least I'm writing it with a capital log. I know this can get a little confusing. We have the log of z, the multi-valued function log of z, we have the real valued function natural log of z, and then we have the principal branch, which I'm using capital log z, where you're taking n equals 0. So you may want to take a moment to just take that. And other books will use different notations that are equally hard to absorb, but it doesn't seem to be any way around it. You basically have three things here: the multi-valued function for log, the real valued function upon which it's based, and then a principal branch. Yeah, so I have an example here, taking the log of 1 plus I, the square root of 3. You need to write this in terms of polar form. So first you take the modulus, and that's the square root of 1 squared plus the square root of 3 squared, which is 3. So the square root of that is 2. Then if you put this on a graph, 1 plus I square root of 3, you'll see it's a 60-degree or pi over 3 angle. That gives you this term here. And then you have the repeating part of it. Every 2 pi you repeat. Yeah, and what I just said is here, if you write 1 plus I times the square root of 3 in polar form, you have this quantity here. On this slide, we have two properties for complex logarithms. The first one is the log of the product is the sum of the logs. And the second one is the log of the quotient is the difference of the logs. So these should look familiar. They're the same as what you have for real valued functions. And we'll make use of this one actually in the example in the next slide. On this slide, we do a few examples. The definition of the log I pasted up here just so to remind us. So we'll take the log of minus 1 minus I as a first example. And that's using the definition here, the natural log of minus 1 minus I, but the modulus of this is just minus 1 squared plus minus I squared, which is 2. So we get the square root of 2. And the angle is basically in the third quadrant. If we assume our argument here is between 0 and 2 pi, then the angle would be 5 pi over 4, basically a pi over 4 angle in the third quadrant. And then we have our I 2 pi n factor here. So that's our first example. Our second example is we'll just add this to itself. That's why I had z1 and z sub 2 here. So this is our z1, this is our z sub 2. We add it to itself. We get 2 log of the square root, 2 the natural log of the square root of 2 plus this added to itself, 5 pi over 2 I. And then we have the repeating term. I put these as different because we actually need to set it to a different value than what you would set here. They're not in sync, so to speak. You see the problem here is that if we define our principal argument to be between 0 and 2 pi in this set of examples, then this is bigger than 2 pi, so we need to normalize that, and it would actually be putting in a minus 1 here to give us a pi over 2, and then we would be within the bounds of the principal argument. That becomes even more obvious when you multiply the z1 times z2 here, multiply the number times itself. Notice the log of the product is the sum of the logs, so you would expect these to be the same. And so when you multiply this together, you get the minus I times the minus 1 and the minus I times the minus 1. That gives us 2I, but the minus 1 times minus 1 is a 1, and the minus I times the minus I is a minus 1, so that cancels. You just get the log of 2I. The modulus is 2, and the angle, the argument is pi over 2. So you can see, the issue we had here. We needed to, they're not equal, but unless we adjust the value of m and s here. So if we let m equal minus 1 and then s equals 0, then these two line up. Okay, we're just going over something on this slide that we talked about in lesson 2. If you recall, we had this figure, and the point was that the argument has a discontinuity along the negative real axis if we define the principal argument to be between minus pi and pi. So the argument at this point as you approach, as epsilon approaches 0 is pi, but the argument at this point as epsilon approaches 0 is minus pi. So you get for any point on either side of this this line, you have a jump, you have a discontinuity in the value of the argument. And the point here is that that carries over to the log of z because we define the log of z in terms of the argument of z. The other point to be made here is that if we change the principal argument of z, then for example to be between 0 and 2 pi, then the discontinuity for both the argument and the log of z would be along the positive real axis. But there's other cases where you need to, no matter what you do, you're going to have that discontinuity. And there are other cases where you might need to define it along the negative imaginary axis, in which case you would go between minus pi over 2 and positive 3 pi over 2. So just something to keep in mind. If you're working with the log function and you're getting things that don't add up, you might want to consider looking at the branch that you're working on, and that is likely to be the heart of the problem that you're running into. Okay, we're going to take the derivative of log z here. So to start the proof, we take log of z equals w, and that gives us e to the w equals z, or we can write also e to the log of z equals z, noting that the exponential is the inverse of the log and vice versa. We take the derivatives of both sides of this equation here. So the derivative of z, of course, is 1. And we just leave this the way it is here, so we get this expression here. Then if we apply the chain rule to this, we have e to the log of z, then times the derivative of what's in here, in this case log z, derivative log z. And we know this is z, so we have z here, times the derivative of log z equals 1. And then just dividing by z, we get the derivative of log z equals 1 over z. So it's the same as the real valued version of the log function.